In this video, we'll be focusing on vectors. So we have two different kinds of formats of writing vectors. So one is our row vector format, and there's 3 examples, and also our column vector format, and there's another 3 examples. These are really just 2 different ways to talk about vectors and write down vectors. So the row vectors, we use parentheses and separate the numbers by commas. And the column vectors should remind you more of the matrix format, a matrix with 1 column, right? And there's just different styles, different formats here. And a lot of times when we're working with matrices, we like to use the column vector format. And if you remember when we wrote solutions to system equations, we use this row vector format because we'd like to think about the row vectors as like coordinates in 2 dimensions or 3 dimensions or higher dimensions. All right, and you'll also see the notation R2, which means all ordered pairs of real numbers. So a few examples of vectors in R2 would be like the vector 0, 0, or 1, 1, or 1, 2, or just any 2 numbers, right? And the order does matter. So that's what we mean by ordered pair. So the vector 1, 2 is different than the vector 2, 1. So any vector with 2 elements where the numbers are real numbers is a vector in R2. Right? R2 is a set of all vectors, and so all ordered pairs of real numbers. All right, then R3, just bump it up a dimension. R3 means all ordered triples of real numbers. Right, so an example would be 0, 0, 0, or 1, 0, 3, or 3, 0, 1, right? And those last 2 I just said are different, right? Because the order does matter. But all vectors with 3 elements, that set of all vectors with 3 elements is what we call R3. All right, let's focus on our 2 first row vectors. And let's graph them. This is a nice way to think about vectors is by graphing them. So let's graph the first vector. 3, negative 2 just means we go horizontal from the origin, 3 units, and then the negative 2 as the second element means we go down to the vertical direction from the origin. And so that arrow really is the point that is the vector, right? The point 3, negative 2. And we usually like to use an arrow to make it more obvious. That arrow that always starts from the origin and ends at the point. So that arrow can also represent the vector 3, negative 2. Right, we can graph the vector 1, 2, 3. Where we go 1 in the x1 direction, or we can think of it as like the x direction, 2 in the x2 direction, you can think of it as the y direction, and 3 in the x3 direction, which you can think of as the z direction. Right? But when we go into higher dimensions, we like to use the subscripts with the x, so x1, x2, x3, x4, x5, and so on, instead of pulling more letters from our alphabet. It's just easier that way. All right, so that's graphing vectors. Let's focus on the 3, negative 2 vector now. All right, and let's introduce another vector and call it v. And I'll plot that, right? The vector v is 0, 1. So that's plotted there. And what we can do is define addition on vectors, and we're just adding corresponding entries. Right? So if you add u and v together, you get 3, negative 1 by adding those corresponding entries. So 3 plus 0 is 3, negative 2 plus 1 is negative 1. We can plot that result of 3, negative 1 with that point and use an arrow to represent that vector u plus v. And another thing that we can notice is that summation of u and v forms a parallelogram, where the vector u plus v is that diagonal of the parallelogram. That's because a way to think about the summation of vectors is, well, if you start at the origin and so you got 0, 0, and you add u, that gets you to 3, negative 2, right? That is the vector u, 3, negative 2. And then if you start where you left off, right, start at the end of u, and add the vector v, so add 0, 1, that means you're going vertical by 1 unit. And so you can think of addition of vectors as stacking vectors on top of each other. and you get that parallelogram. Right? You could also start with v and then add u. So think about placing the vector u on where you left off with v. So you go up with v, then down and to the right with u. That would also land you at u plus v, right? And it forms this parallelogram. So that's adding vectors. Another thing we can do is scale vectors. So for example, we could scale the vector u by negative 0.5. Right? And what we mean by that is scale each element in the vector u by negative 0.5. So you get negative 1.5 and 1 as the two elements in my new vector. We can graph that vector, and notice if you just purely scale a vector, it remains parallel to the original vector, right? You can think of it as that new vector that's scaled by negative 0.5 on the same line as the vector u. If you had a line going through the origin and through the point u. So it stays on that same line. You can think of any scalar multiple. If you scale, if you scaled the vector u by 2, you'd be stretching the vector u. If you scale it by a number less than 1, between negative 1 and 1, you're shrinking the vector u. When you scale by a negative number, you're flipping the vector over the origin. So you can think about all the different scenarios of scaling a vector. All right, so we've looked at adding vectors and scaling vectors. We're going to look at one more thing, which pretty much just combines these two operations. So let's look at that now. Whenever we scale and add vectors together, we call that a linear combination of those vectors. So one example would be scaling the vector u by 0.5, scaling the vector v by 3, and then adding them together. Right? So you can imagine scaling each vector like we did before, then adding them together, right? Add the corresponding elements. In this case, we'd get the vector 1.52. So there is the linear combination graphed on the same graph as u and v. Another example would be minus u minus 5v. Right? So minus u would be negative 3, 2. So that'd be minus u. And then minus 5v would be 0 minus 5. And you add those together, and you get the new vector, negative 3, negative 3. Right? So that is plotted there. Those are both linear combinations of the vectors u and v. Again, linear combination just means you scale your vectors and then add them up, and that would be a particular linear combination of those vectors. Now, to foreshadow what we'll do in future videos and future homeworks, is we'll be thinking about the entire set of all linear combinations of certain vectors. So if you think about these two vectors, u and v, and think about all linear combinations you could do with these, which means all scaling and adding up of these two vectors, what set does that give you? And just to foreshadow a little bit, if you look at all linear combinations of these two vectors, you could get any vector in R2. It would give you all of R2, right? Another way to think about that is if I give you any vector on my graph, you could figure out a way to linearly combine the vectors to get you that point that I plotted, right? You could figure out how to scale and add up those two vectors to give you any vector in R2. Right? We'll talk more about that in future videos. That's just a little foreshadowing for you there. Another big question will be if you have a set of vectors, maybe two vectors like this, or maybe 3 or 4 vectors, and you're given some point, a big question will be, is that point actually a linear combination? So maybe sometimes it's impossible to linearly combine vectors to give you that point that you're considering. So those will all be future questions that we'll tackle. All right, that's it for this video. Thank you.